All right, let's take a trip. We're going to go to the very, very bottom of reality. And we're going to find out that the rules that govern everything, well, they're not just strange. They're both way simpler and way more random than you could ever imagine.
So, let me ask you something to get us started. What do you think is harder to figure out, mathematically speaking? The chaotic dance of 3 billiard balls bouncing around a table, or the inner workings of just one single atom? I'm willing to bet the answer is not what you think it is.
And that's because, and this is our first big surprise, when you get down to the quantum level, the math doesn't get messier. Nope. In a really important way, it actually gets cleaner, simpler.
And here it is, that 3 billion ball problem. In classical physics, it's called the three-body problem, and it's a legendary nightmare. It's nonlinear, which means it's basically unsolvable. It's a total mess. But the Schrödinger equation, the absolute bedrock of quantum mechanics, it's linear, and that simple fact makes it, mathematically speaking, way more elegant and manageable.
So what on earth does linear even mean? Well, it's this incredibly powerful property. Think of it like this. If you have two separate correct answers to a linear problem, you can literally just add them together, and you get a third, brand new, perfectly correct answer. The solutions all just get along without messing each other up.
Here's a perfect real-world example. You've got a single fiber optic cable with millions of different phone calls streaming through it at the same time. Every single one of those calls is its own solution. And because the physics is linear, they all travel right alongside each other in that one tiny cable and don't get jumbled up. They just add up. That's kind of how quantum mechanics works.
Okay, so the math is simpler. It's linear. Got it. But this is the point in the story where things take a hard left turn into the truly bizarre. Because to make all this beautiful, linear math work, physicists had to build our reality on a foundation of numbers that, well, aren't even real.
Take another look at the equation. This is the engine of the quantum world. You've got symbols for energy and time and the wave function. And then you've got that little guy sitting right out front, the letter I. And I stands for the square root of -1, an imaginary number. And let me be clear, this isn't just some clever math trick that you can cancel out later. It is baked in. The wave function, psi, the thing that literally describes the state of a particle, it has to be a complex number. It needs that I. If you try to write the theory without it, the whole thing just collapses. It doesn't work.
So this is the puzzle, right? We live in a world of real things. You can't have an imaginary number of apples. So how can the fundamental theory of our real world depend so completely on numbers that we call imaginary? What does that even mean?
Well, a physicist named Max Born came up with the answer to the imaginary number problem. But his solution, while brilliant, came at a staggering cost. It blew up one of the core principles of all of science, the idea that we can predict the future.
So here's what Born figured out. You never actually see or measure the wave function psi itself. Instead, you do a little mathematical trick to it that, poof, makes the imaginary number I disappear. And what you're left with isn't the particle's location. Nope. What you get is the probability of finding it there. Just the odds.
Now you might think this is weird, but you know who thought it was absolutely ridiculous? Erwin Schrödinger, the guy whose name is on the equation. He hated the probability idea so much that he came up with his whole Schrödinger's cat thought experiment just to show everyone how absurd it was. He was basically saying, look, this can't be right. And you can see this randomness in a simple experiment. Send a horizontally polarized photon at a horizontal filter, and 100% of the time it goes through. Makes perfect sense. But now take a diagonally polarized photon. Every single one of these photons is prepared in the exact same way. They are identical. And yet, when they hit that same filter, sometimes they go through and sometimes they don't. It's a coin flip. The exact same starting condition is producing different results. This fundamental randomness is what drove Albert Einstein nuts. He's the one who famously declared, God does not play dice. He just couldn't accept it. He believed there had to be something deeper, something we were missing that would make sense of all this chaos. So Einstein came up with this idea. What if quantum mechanics is just incomplete? What if those identical photons aren't really identical? Maybe they have some secret internal instruction, a hidden variable that we just can't see, telling one to pass through the filter and the other to bounce off. Maybe the randomness is just an illusion. For years, that was just a philosophical argument. Nobody knew how to test it. But then, in 1964, a physicist named John Bell did something incredible. He came up with a mathematical test, a theorem, that could actually prove whether these hidden variables existed or not. And starting in the 1970s, scientists started running the experiments, and the results all pointed to the same shocking answer. Bell's theorem was violated time and time again. The experiments were crystal clear. Einstein was wrong. There are no hidden variables. The randomness isn't a cloak for our ignorance. It is a fundamental, non-negotiable feature of our universe. There's just no way around it.
So where does that leave us? We've gone from a simple linear equation to a reality built on imaginary numbers that's fundamentally unpredictable. We're left with a whole new rule book for how the universe actually works. So let's just lay out this new quantum framework. Number 1, reality is linear. Different possibilities can exist at the same time and just add up. Number 2, it's complex. You need imaginary numbers to describe it. And number 3, it's probabilistic. Deep down, the universe runs on chance, and the best we can ever do is calculate the odds.
And the most important thing to get is that this isn't some temporary placeholder theory. This isn't our best guess for now. Quantum mechanics has been tested more rigorously than any other idea in science. It is the operating system of the universe. As far as we know, this really is it.
Which leaves us with a final, absolutely mind-melting question. The math tells us that before we look, a particle exists in a haze of possibilities. It's only when we make a measurement that reality snaps into focus and picks one outcome. So, if things only become definite when we observe them, what does it even mean for something to exist when we're not looking?